Hello everyone, welcome to this video. This time we're going to be solving the problem 2.22 as it appears on Introduction to Quantum Mechanics edition. So this problem states that suppose that we have a free particle that is initially given by the wave function at time equals 0, right? Initially, a to the e minus small a x squared. And given this, we want to determine if the uncertainty principle holds, and if it does, determine at what time the system comes close. So what we have to find here is basically sigma x sigma p, and make sure that this is indeed greater or equal than h bar divided by 2. So in order to find this, we're going to need the sigmas, right? In sigma x, so this is just value of x squared minus the value of x squared, and similarly for p. So first we're going to need those 4 expectation values. But to find the expectation values, we need the probability density of our function. But in order to do that, we're going to need this function as a function of time, right? This wave function, because right now we only have what it is in the first moment. And in order to find that, remember, we're going to need now the phi k function. That, remember, we discussed it previously. This is basically like these ends that we had in the case of the. And to find that, first we need to normalize this wave function so that we can find a. So let's begin by doing that. Let us just go ahead and normalize this wave function. So we got that 1 is going to be equal to the interval from minus infinity to infinity of a squared e to the minus a squared dx, right? I just squared this wave function because it's real. So this is right, the modulus of a squared. So this integral will just be this a squared, can just come outside, and it's just a Gaussian integral as we have seen many times before. This is just the square root of pi divided by 2a, right? We have seen many integrals of this type before. This is going to be equal to 1, so from there we see that a is going to be 2a divided by pi to the 1/4 power. Okay, so that is the constant of integral. So now we need to go ahead and find our phi of k. So our phi of k, remember, is going to be 1 divided by the root of 2 pi, integral from minus infinity to infinity of this wave function phi of x comma 0, x comma 0 times e to the minus I ax dx. So let us now write in here our expression for psi. Psi is just a times e to the minus a. Let me double check. That's what it was, right? Yes. Okay. So now we need to integrate this. So let us pull the a outside. I could also just write the value for a, but it's just quicker to just leave it like this for now until we write. So this is going to be integral from minus infinity to infinity e to the minus a squared plus I ax dx. Okay, so now we need to get this integral solved somehow. So how do we do that? The easiest way, at least for me, and I think that it is the easiest way, is to try to turn this into something of the form e to the minus squared d, right? Because this is going to be just a Gaussian integral, and we know what that is. So in order to do it, and why do we know that we have to get to that? Because there's x squared here and an x here, so we could just go ahead and complete the square here, right? So in order to do that, well, I hope you're all familiar with the procedure. It's not really complicated, and I will explain it, but the first step is just to leave the x alone here. So we're going to factor out the a. So we get minus a x squared. So we have to now divide here by a. So that when we multiply this inside, we get what we had before. Okay, so now what we usually do here is, since we know that, right, a squared plus the other way out, a plus b squared is just a squared plus 2ab plus b squared. So in this case, we have the a squared and we have ab, right? So usually what we do here, and this is quite typical in this sort of problem, is that we are going to say, okay, so this x squared plus I kx divided by a is going to be the same as x plus I kx divided by 2 squared, right? Because when we square this, we're going to get the x squared from here, then we're going to get, sorry, this x does not belong there, it's just ik, because then the second term will be 2 times x times ik divided by 2a. So when we do that multiplication, we are going to get what we have here. But then we have an extra term, right? This term squared, which is minus a divided by 2a squared. So minus k squared divided by 2 squared a squared. So we need to now subtract that. So we have to subtract by minus a squared divided by 4a squared, so that we can compensate for the fact that we have this extra term. Okay, so this is what we are looking for. So now we can plug it in there. So we get 1 divided by the square root of pi times a, that goes from minus infinity to infinity, e to the minus a times this whole thing, big bracket, times x plus I k divided by 2a squared plus a squared divided by 4a squared dx. But now we can separate these two, just multiply through by the a, and we get this first one right here, and then we get e to this thing right here, but with minus times minus a. So the minus sign in front and the a squared will cancel out with this a. So we get now minus k squared divided by 4a. And since this does not depend on x, we can just go ahead and pull it outside of the integral. So we get 1 divided by the square root of 2 pi times a times e to the minus squared divided by 4a. Now comes the integral from minus infinity to infinity of e to the minus a x plus ik divided, only this here is divided by 2a squared dx. So here we can introduce the change of variables. This is just a standard way to do this integral. 2 is going to be equal to x plus I k divided by 2a. So du is just going to be dx, because all of this is a constant. So the integral will now be minus a, and all of this right here will just be u squared. And dx, this will be du. So this is now a Gaussian integral. So that is the trick that we had to use, because we began with this right here, and the trick is that you have to see, oh, here we can complete the square. So then we complete the square, so we can get to this right here, where it is x plus or minus something, and then we just make a substitution, and well, that's going to be the way to do it. So this is just going to be our constant right here. I'm going to write out what we had for a now, which was, let me double check, it was 2a divided by pi, and this to the 1/4 power, and then we have e to the minus squared divided by a, and then we have this integral that we now solved, which is just going to be square root of pi divided by square root. Okay, so well, now we have to see if there's anything we can try here, but so I got a bit more room. So our phi of k is going to be this. So let's see. We got this square root of pi right here, which is going to cancel out this square root of pi right here. And then we have this square root of 2, and there's 2 to the 1/4. What we are going to get from that is going to be 1 divided by 2 to the 1/4 power. And well, there's still that pi, So we actually should put it in here, so together, so we get 1 divided by 2 pi, 1/4 power, and then we have this a to the 1/4, and there's this divided by a. So, well, I'm just going to put it all together because there's now also an a that is to the 1/4 power. We get 1 divided by 2 pi a 1/4 power. Okay, what did we use? We use this pi, we use this to this, a, and this. So all there is still to put this exponent. Okay, so this is our phi of k. And this is going to be what we have to put into our expression for psi of x comma t. So as we remember from the formula from last time, which is basically the way to write down the most general solution for the free particle, this is going to be 1 divided by the square root of pi. This is just that normalization constant, integral from minus infinity to infinity. Then what we have our phi of k, which is just 1 divided by 2 pi a 1/4 power minus a squared divided by 4a. Now we have to multiply this by e to the I x, e to the minus I, and this is I e t divided by h bar, right? But we know what the energies are, so this is going to be h bar a squared divided by m, and this whole thing will be integrated with respect to k. And because we are adding over all of the possible values of k, which is related to the velocity of this. So now we need to solve this other integral, which is also going to be a little bit nasty, but well, that's what I'm here for. I'm going to copy it. Well, great. So now we need to solve this. So this is going to be, let's just put these constants up front. So we get 1 divided by the square root of pi times 1 divided by 2 pi a to 1/4 power. Then we get integral of minus infinity to infinity. Let us now factor these terms in the exponential. So we get e to the minus, and let's now factor out the things here that have k squared. So k squared 1 divided by 4a is positive because minus is now outside, plus I h bar e divided by m. Okay, yeah. And then we have this right here. So minus I a x dk. Okay, so now we need to work this. This is in the same form as what we had previously. All right, so there is actually a formula that you could use because these integrals are all of the same form as we have seen in previous cases with other integrals. But since it is probably the second time you are seeing this, let's just work through it so that I make sure that you know how to. Okay, so first things first, we are going to have to isolate the k squared. So in order to do that, let me now rewrite this. Just add these two fractions to. So we are going to get m plus, because we need to multiply this by 2m, no, only by m. Our denominator will be 4am. This has to be multiplied by 2a, so we get 2a I bar divided by 4a. That's going to be our exponent. I mean, this part of the exponent. So this is going to be m a I h bar divided by m. So what we want to do now is we want to isolate the squared so that we can complete the square easier. You don't really have to isolate it, but I think that it's easier to do it like this when you are first the sort of problem. Once you've done it more times, you can just skip a few steps and it's going to work out just. So I'm going to write out these constants. They are not going to be changing for now. 2 pi a to the 1/4 power integral from minus infinity to infinity of e to the minus, and now we have to put this term that we have now factored out. So m plus 2a h bar t divided by 4am, and this is multiplying what we had inside. So k squared, then we have minus I a x, and then this has to be divided by this quantity, 4am divided by plus ai h bar t. Okay, so now we can complete the square. So how do we do that? Exactly the same as before. I'm going to do it a bit faster this time because there's something that I hope previously, and we also did it in this video already. So let's see, we're going to do it e to the minus, the same thing, m plus 2ai bar t divided by am. Now this is going to be multiplied by k minus what we have here, but now divided by 2 and without the k. Remember, now we are isolating, completing the square for k. Before we did it for x, so don't be confused, because now the integral will be with respect to k, not to x. Get k minus I times 2. It's no longer a 4 because we have to divide this by am divided by m plus ai, this squared, and now we need to subtract from this minus, well, this squared, so that is going to be, well, a minus sign because of the I, so another minus here, and then we have 4x squared a squared m squared divided by m plus ai h bar t squared, and this has to be multiplied by this factor right here that was multiplying the entire thing. Before we multiplied by minus a, now we have to multiply by minus. When we multiply by this, if you see, the numerator here will cancel out the square in the denominator right here. Then this 4 will cancel out this 4. A will cancel this squared, the m will cancel out this, and we have another minus sign. Minus, minus, minus. The end is going to be minus. So minus right here, cancel out by that other. Okay, and since now we are subtracting this other thing, we can just write it as another exponential, e to the minus this thing. Okay, so that was hopefully not too confusing, but I know that there's like a lot of integration to do. There's going to be a lot of constants around. This square right here didn't come with a copy paste, so make sure that we are all good. So now what we have to do, well, there are several things. First, you're going to have this is equal to 1 divided by square root of 5, 1 divided by 2 by a 1/4. And now this exponential does not depend on k, so it's just a constant with respect to k, so we can just pull it out of the integral. So we get e to the minus x squared am divided by m plus 2ai h bar t. But as you can see, this whole thing, m plus 2ai h bar t, this comes up quite often in our integrals. So let us now multiply this by 1 over m divided by 1 over m, so with the objective of writing it like this. So the m's will cancel out here, so we get 1 divided by this divided by m. So now it looks a little bit cleaner, and what we can do now is say, okay, let us now define the quantity. Theta is going to be 2h bar a t, is what we have here, divided by m. Okay, so when we do that, this exponential will just be minus x squared a divided by 1 plus I theta. Okay, so now it does look quite a bit cleaner. So now we have this integral from minus infinity to infinity, And then we have e to the minus, and as you can see, this is basically the same that we have here, so we can just divide by m in the numerator and denominator, so we get 1 plus 2ai h bar t divided by 4a, and this is divided by m. So here we can also write, well, maybe I should have erased it, but remember theta is just 2 h bar a t divided by m. So here this is also going to be theta times I. So this here is just theta times I, or just I theta. And then we can just use a change of variables right here. So this here is just a constant, so we can say 2 is going to be k minus 2i x a m plus 2ai h bar t. There's no need to put theta in here because the u will just be dk. Okay, that's just a shift. It's just basically moving. Gaussian interval is not really a variable, so this interval will now be e to the u. Sorry, I already had the exponential, so it's going to be e to the minus this u squared eu. So this interval is just a Gaussian interval. So we have managed to change the form of the interval to the one that we wanted. Now we can just all of these constants right here, e minus x squared a 1 plus I theta, and this is just square root of pi divided by the square root of this. But since it is a fraction, the 4a will go to the numerator and we get 1 plus I theta. Okay, so what simplifications can we make? First, there's this pi will cancel out this pi right here. This 4 is just going to be 2 times 2, so it's basically 2 times square root of 2. So one of them will cancel out this square root of 2 right here, so we can change this 4 for just a 2. And well, and then what we can also do is this a is the square root of a divided by 4th root of. So let me just write it down. It's going to be a divided by, and then we have also this 2 square root of 2, so the 2 will also be here in the numerator. 2a divided by pi. This is going to be to 1 power. Right, let me make sure that, yeah, that I this into consideration, this a and this a and this 2. So I still have to put this 1 divided by square root 1 plus I theta and minus x squared a 1 plus I theta. Okay, so this right here is our function. So let me just go to the next page so that I can write it out a bit cleaner. This right here are psi of x and t. Okay. And I'm this here. This is a 1. I'm just going to tidy it up a little bit. 1 plus I theta. Okay, so I'm just going to make a quick pause to make sure that I have not made any silly mistakes so far. So it is 2a to the 1/4 power divided by pi e to the minus ax squared divided by 1 plus I theta divided by, okay, so far so good. So next what we want to do is we want to find the probability density. So how do we find the probability? So as we have said before, it's going to be the probability density will be psi conjugate times. So when we do it here, this first term is real, so it's just going to be that term. So 2a divided by pi 1/2. Now this right here is not real, so we are going to have to consider its conjugate multiplied by that actual thing. So it's going to be 1 minus I theta multiplying the square root of 1 plus I theta. So that is that part, and then we have the exponential, where there's also an imaginary part. The conjugate will be 1 minus, and then we have e to the minus squared a divided by 1 plus I theta. And because we're multiplying on the exponentials, we can just add the exponents. So now we need to make sure to calculate this quantity. So first we have 1 minus I theta times 1 plus I theta. Now this is just going to be 1 plus theta squared, right? And then in the second part we can factor out in this exponent, we can factor out minus x squared a. We get 1 divided by 1 minus I theta plus 1 divided by 1 plus I theta. And when we do that, we can now just add up this fraction here. So we get 1, well, let's first put this minus x a, and then we get 1 plus I theta plus 1 minus this I theta, so I theta. And all of this is going to be divided by the product of these two things, which, as we already saw, is just 1 plus theta squared. So in here, these I thetas will cancel out, and then you got 1 plus 1, which is just going to be. So now we can put all of this into this expression right here. Get, well, this part times 1 divided by the square root of 1 plus s. And then we have the exponential here. As we also saw, it's just e to the minus a x squared divided by 1 plus s squared. Okay, so this is the expression for this probability density. Now, because we are going to have to continue working with it, it is going to be convenient to make yet another change of variable just to make this notation better. So as we can see, there's this a divided by 1 plus theta here, and down here we got the square root of a divided by the square root of 1 plus theta squared. So we can introduce the new variable or constant w, which is a divided by 1 plus theta squared square root. So when we do that, we get that, let's write it like this, psi x comma t probability density going to be, now instead of 2a divided by pi, we just give the 2 and pi together to the 1/2, and then this right here is square root of a divided by 1 plus theta squared, which is just w, so w, and then we have e to minus 2 times w squared, because the normal w what with the square root, we don't have that, times x squared. So this is a notation that is a lot cleaner than what we did before, so that is obviously going to be better for us to work with. If you hadn't thought of making this change of variables, then don't worry, because I mean, you could still do the next steps obviously, but it will be somewhat messier because there will be more constants lying around. Now we finally found this, and what we have to do now is begin finding the expectation values. Now I do want to make just a quick stop here to discuss what happens with this probability function as time continues. So in the first instant of time, what this is going to be a function but like this, here centered around x0, and as time is going to be moving forward, this will be flattening out. Okay, whoops, I did like, so you can see that our probability density is going to be flattening out in later times, which is what we expect for a free particle. It may begin somewhere, but as time goes on, it is spreading out. It is a wave that spreads out. So I would just want to make a quick comment. So let us now find the expectation value of x using this. We know that this is just going to be the integral from minus infinity of x times our I squared dx. And this, no integration allowed here. This is just 0. because it's going to be an odd function. Then x is odd, so this is just going to be 0, right? I have told you in previous videos how important it is to know to distinguish an even function from an odd function, because it would save you a lot of time, right? This would have been an annoying integral to do, and we can see that it's just 0 so quickly. So now we have to find the expectation value of the momentum. Now this is not a stationary state, so we can't say, oh, it's 0, right? So you can either calculate it, or you can write it as momentum. The momentum is going to be the mass of the particle times the values of its velocity. But we know that instead of velocity, we like to talk about the time derivative of the value of position. However, this is 0, so it does end up being 0. But you can't really say that it is because, right? So these two values are 0. We found them very, very quick. Well, let us now take a look at x squared, at the expectation value of x squared. So it's going to be minus infinity x squared times right here. That's going to be 2 divided by pi, the 1/2 power. That's why I calculated this before doing these integrals, because the integrals themselves are going to be messy. So it is good to have found this quantity before. So we got x squared 2 divided by pi w e to the minus w squared x squared dx. So this is something of form that we have seen in the past previous video. So let's put all the constant outside so that it is more apparent. Divided by pi power w integral of minus infinity x squared e squared dx. Okay, so this integral we have seen I'm going to do it anyways the long way. I have previously just stated the result, but just in case, because this was quite a few videos ago, so I'm going to just do it again in case anyone forgot or didn't see it. So the way to solve this, the constant is, we say, okay, we are going to call this 2w squared, let's just call it beta. And if we were to derive with respect to beta the function the minus beta x squared, oh, it's I'm covering up with the, sorry, let me, so if we were to derive with respect to beta e to the minus beta x squared, we would get minus x squared minus x squared. Yeah, I'm covering up with the camera again. Okay, we would just get that right there, which is what is inside of our integral, except by that minus sign. So we can now write it as minus the derivative with respect to beta integral from minus infinity. We can pull the derivative out of the integral because it's with respect to a different variable of, and this is multiplication, not subtracting, e to the minus beta squared. So now this is just a Gaussian integral. That's why we did this whole thing. Get minus 2 divided by pi to the 1/2 w, and then we get the derivative with respect to beta of the integral of this, which is the square root of pi divided by the square root of beta. But when we take this derivative, right, well, pi, square root of pi is just a constant, and in fact it's going to cancel out the square root that is here, square root of 2. So this is going to be the derivative with respect to time to beta of beta to the minus 1/2. So we're minus 1/2 beta to the minus 3/2. So the minus signs will now cancel out. So it's going to be positive. And well, now let's just go to the next slide and we can continue working there. That this expectation value of x squared, it is square root of times w. I already forgot the rest. Let's put the 1/2 here, and then we have, it was a beta, but beta is 2w squared, and this is divided by power. It was negative, but that's why I just wrote 1 divided by. Okay, so now we just have to simplify this. I like to write it as, whenever I have that to the 3/2 power, I just like to write it down as 1 squared multiplied by 1 without the square. Right? It's the same. That is to the 3/2 power. So now you can see we got this square root of 2 right here. That will cancel out this square root of 2. The square root cancel out this power, so we get here just w, which will cancel out with the w up there. So now we get 1 divided by 4w squared as our result for the expectation value of x squared. Okay, so let's order. Okay, so we are doing so far well. Now let's just go ahead and look at the expectation value of p squared. Now we know that this is going to be minus h bar squared minus infinity to infinity of psi conjugate times derivative of the squared of psi. So here we are going to find, first we need to find this quantity and then multiply it by this conjugate, and then we can integrate. We could do it all inside the integral, but I think it's just going to be even messy. So what was our psi? Our psi was just, it was 2a pi to the 1/4 power times 1 divided by square root of 1 plus I theta. Well, we had actually used a few different notations back then, but it's okay. E to the minus, and well, actually let me take a look at what it was exactly. I don't want to try and do this by memory. So psi of x, where was that 4, that 5? There we go. So this was our result, 2a to the 1/4 power. Okay, right. So this was it. I'm just going to copy it actually. Are we here? That was the result that we had. Now we had still a few different notations that we put here, but basically that was it. So we have to now derive this twice. So just to make the notation cleaner, we are going to use the following notation. So instead of that whole constant, we're just going to say this is b. So b is going to be equal to 2a divided by pi, the 1/4 power, and times 1 divided by 1 plus I theta inside of this. Right? We can't just call this w, right? Because this is a to the 1/4 power, not a to 1/2, and this is not I plus theta squared. Right? And so it kind of looks like when we use the w, but it's not the same. And here in the exponential, we can define small b as a divided by 1 plus I theta, so that we get e to the minus b x squared. So that is going to mean that our notation will be a lot better, so we can also do these derivations much better. So the first derivative is going to be minus 2b times large B x to the minus bx squared. So we do it when we derive again. So basically second derivative here. So now we're going to get a product rule. So we get minus 2 small b large b to the minus b squared. Here we just derive the bx. Then we get plus 4b squared x squared e to the minus bx squared. Okay, so let us now take this to the next. This is our second derivative, but we can still make this a bit cleaner. So we can factor out the exponential. Let's just write to the right. And oh, I think I'm missing this large b here, by the way. Yeah, I'm missing the large b. About that. So we can just factor out large b. We can this write it as minus 2b large b So we get here 1 because the exponential will go to the other side. We get minus 2bx squared e to the minus bx squared. There we go. So we factor it out a bit more. Now it looks a bit better. Now that we have this, in order to compute the integral, we still need to multiply this. Where were we here? With psi conjugate, right? So you need to see this product. Now, psi conjugate is going to be b conjugate, because remember our wave function is b e to the minus bx squared. So it's going to be b conjugate e to the minus small b conjugate x squared. And this is something that we have to now multiply by all of these things times minus b, a large B, 1 minus e x minus. Okay, so here there's two main things that we have to look at. We are going to have the product b conjugate b, which is just going to be absolute value of b squared. And since b was 2a pi to the 1/4 power times 1 divided by square root of 1 plus I theta, that's b. So b conjugate, this part will be the same, but this will flip, so we get 1 minus I theta times the same thing. So we're going to have the square root of 1 plus I theta, and this will be squared. So instead of being 1/4 power, it's going to be 1/2. So this is just going to be a divided by pi 1/2 power times 1 divided by the root of 1 plus squared. That is the product of b conjugate b. Now in the exponentials, we're going to get e to the minus x squared factor of conjugate plus b. So let us take a look at what that is. Conjugate plus b. Considering that b was a divided by 1 plus I theta, then the conjugate is going to be 1 minus I theta. So here we can factor out a, and we get 1 divided by 1 minus I theta plus 1 divided by 1 plus I theta. So here we can now, this is actually exactly the same that we found previously. So this is just going to be 2 divided by 1 plus theta squared. So now we can just go ahead and plug all of that into this expression right here. So instead of, well, I think I'm just going to go to the next, otherwise it will be messier because I think it's already kind of hard to follow. So that I'm going to need to this it will along go, and the expressions that we found, this right here is modulus squared. Also had so let's put all of this into this equation right here. So the b's will multiply, so we get 2a pi the 1/2 power times 1 divided by square root of 1 plus squared. Then we got this whole parenthesis thing going on, minus small b 1 minus squared, and the exponentials now are going to be e to the minus a, so 2a divided by 1 plus theta squared x squared. But remember, previously we defined w to be the square root of a 1 plus theta squared. So we can actually simplify this a little bit, because this a and this thing right here will just be w, and in the exponent it's going to be minus 2w squared x squared. So this made the notation somewhat cleaner. And well, this is something that we can actually work with now, and we can actually go ahead and perform the integral that we want to do. the expectation value of p squared, this is just going to be, well, we had minus h bar squared times integral of what we have here. So let me actually just pull all of our constants outside. So we divide it by pi square root w, and then we have this minus 2b. So the minus will cancel out, get times b, and now everything else just goes inside the minus of 1 minus 2b squared e to the minus 2 w squared x. Okay, so here we have two integrals. Let's call this I1, I2. First integral is going to be integral from minus infinity of e to the minus 2 w squared x squared dx. This is just a Gaussian integral, as we have seen many times. It's just square root of pi divided by 2 omega squared. Okay, and then we have I2 going to be minus 2b times the integral from minus infinity of x squared e to the minus 2 omega squared dx. So we actually solved this exact integral already when we were doing the value of x squared. Let me see if I can find it. I think it's here. Not the final result yet. 7. So that integral. But that was taken into consideration that. So let me just take a look at that, because I don't want to make a mistake at this point of the video. So this is going to be minus 2b times square root of pi divided by 2 times our beta to the minus 3 halves. So 1 divided by 2 omega squared as power. Okay, so that's going to be this. So you can see that this 2 will cancel out the one waiting outside. So, well, we can now just plug everything into our integral. Go ahead and copy this. So we get constant waiting out here. This is going to be multiplying the result from the first integral, which was just square root of pi divided by 2 w squared, and then we have minus, it was 2b, but now it's just right. Okay, where is it? There we go. I took the minus with it, so we have that minus b times square root of pi divided by 2w squared. Okay. So let me, as before, rewrite this in a way that I find more comfortable. Just for simplification, we do 2w squared root times 2w. So let us see what we can now begin simplifying. So first of all, there's this square root of pi here. Cancel out with these right here. What else do we have? Now there's this w, so this inside the square root is just going to be the square root. Actually, let me just rewrite it rather than writing it. It's going to be 1 divided by w square root of, and right here we can do something similar. This one right here, w times that right there. So now the w that is multiplying here will cancel out this. So let's do this step by step. We get this is h bar squared. There we got a square root of actually that can this get times b 1 minus b divided by. Okay, so here in principle, actually here we already have the answer, but we can simplify this further if we just recall that w, is that the best way to go about it, or just go for, let me take a look. W, this was square root of a divided by 1 plus theta squared. So w squared is this thing without this root. That. And b was, wait a minute. Yeah, b is a divided by 1 plus I theta. So let's see, if we now replace that here, we get 2h bar b 1 minus, let's begin only replacing the w squared, so we a squared down here, get 1 plus, oh, not a squared, just a, 2a, and get 1 plus theta squared over there. So yeah, now we can replace here, let me move this. So now we can replace value of b, 2h bar squared, and b, as we said, is a divided by 1 plus I theta, with 1 minus, then instead of b we get a, and this 1 plus theta squared we can write as 1 plus I theta, 1 minus I theta, and then we have to divide this by the 2a that was already there, but also by what comes inside of the b, which is 1 plus I theta. Okay, we're making progress here. So the a's will cancel out, and also this will cancel out with this. A here will cancel out. Get 2 bar squared a divided by 1 plus I theta. And then we get 1 minus 1 minus divided by 2. And well, here we can just let this 2 multiply so that we get rid of this divided by 2. This here will go away. 1 will be 2. Get 2 minus 1, so that's just going to be 1. And then we have minus I theta, so that's going to be plus I theta. Plus I theta. So now this I theta will cancel out this I theta, and we see that the expectation value of the momentum squared will be h bar squared times a. So this is much simpler than what we have seen here, for example. So, well, now finally found our results for the expectation values of p and x and p squared and x squared. So let us just pull them all here into the screen so we can begin using them. But where's the x squared? 1 divided by 4 w squared. Because x squared was 1 divided by 4 w squared. Okay. So, well, obviously w has its own value, but let us replace it a bit. So now let's do it right away. So it's going to be 1 divided by 4, and w, as we saw before, is, well, w squared, and that's what we have here, is a divided by 1 plus theta squared. Theta is 2h bar a t divided by m. So let's write that in here. So divided by a down here, and this part be 1 plus theta squared, so it's going to be 4 bar squared divided by m squared. So this is actually going to be the expectation value of x squared. So now sigma x, that's just going to be the square root of this, because the square root of x squared minus x squared, but this right here is just 0. Found before. So it's just the square root of our result right here. So it's going to be square root of 1 divided by 4a plus 4 r squared a squared divided by 4a squared. Here we can actually simplify a few things. So this a right here, and cancel out the 4 and the Okay, so that's uncertainty for sigma x. And uncertainty for sigma p is going to be just h bar squared and square root, right? So just h bar times square root of. So the uncertainty principle, now we want to check it. So in this case, sigma x, sigma p would be the product of these. Get h bar square root of a times square root of 1 divided by 4a plus h bar squared a squared m. So this is our result for the uncertainty principle. Now let us see basically what happens at t equals 0, right? So when t is 0 at the initial time, this is going to be the smallest that this expression will ever be, right? Because it's only going to be growing after. So if the uncertainty principle holds at t equals 0, then it will hold at any other time. At t equals 0, we got that sigma x, sigma p at t equals 0 is going to be h bar square root of a, and this whole thing right here will be 0. So we get times square root of 1 divided by 2a. The square roots of a will cancel out, and we get that this is going to be h bar divided by 2. So we see that it's going to be right at the answer. So that was it for this problem. It was a nasty one. So let's just quickly go through what we just did. So what we wanted was to do exactly this: determine if the principle holds or. So in order to do that, we needed to find the expectation values, but for that we needed the wave function, for that we needed the phi of k, and for that we needed the normalization constant. So we began by normalizing. Then we determined phi of k using the formula right here, derived in the previous video. Found phi of k, whoops, this was copied. We found phi of k, we use it to find psi of x comma t, for which we need to solve another integral. Of that integral, and with psi of x comma t, we could in practice begin finding the expectation values. But because the integrals were going to be quite nasty, it is good to determine probability density. That's why we first determined this quantity, and then actually began calculating the expectation values. X and t were quite easy, they were just 0. And then for x squared, we had to do some nastier integrals, and for p, we needed to determine the derivatives first. That's why we have back derivatives, because of the fact we could have just done it all inside the integral, but as I said, it's just messy that way, and in such long integral problems, it's back one step at a time. Then when we found the result of those derivatives, multiply this by conjugate, and well, with that we could just go inside of the integral and just evaluate it, find value of p squared. Then we had to do some algebraic work to find, and then finally we just had to evaluate values, put them in certainties, and we found our result. So, well, if you made it to the end, congratulations. And this was it for the free particle. There's not too much more that can be done at our level. And well, I will see you in the next video, where we begin at other kinds of potentials for the Schrödinger equation.